Alright, so now in this video we're going to look at using an NPN bipolar junction transistor as a constant current source, which means it will provide a constant amount of current depending on the voltage coming into the base, which we generally set with a voltage divider, 2 resistors, or we could use a resistor to limit the current and a Zener diode to limit the voltage, to set the voltage at the base. Any more energy than that voltage will just pass current through the Zener, so it will hold that voltage at a point. And of course we have to remember that the base to emitter always drops about 0.7 volts from whatever input it comes along. So let's start looking at some circuits. So now to start off, we're going to only work with 5 volts. 5 volts or 3.3 volts. We'll see where we get. But we're going to use 5 volts. And I have 2 resistors here. And I find that, let's go to resistance, that I don't want to use probably more than about 1 kilo ohm resistors, 1000 ohm resistors. So there you can see that is 0.982 kilo ohms though. So almost 1000 ohms, 982 ohms. And then over here, this one, again, this is a lot closer, but still about 1000 ohms, 1 kilo ohm. We will apply the power supply to the rail, and since they're equal value resistors, we'll plug it in there. So now we got barrel plugged into the breadboard power supply, plugged into the breadboard. So now it's powering the rails, and we can set the meter to voltage. Of course, since it's equal value resistance, first we'll get the voltage of the rail, so 5 volts, but halfway between the resistors, of course, we got half of the power supply voltage at 2.5 volts. And now zooming in, we're going to grab the transistor. So this is an NPN transistor. It's a 2N2222, and any transistor that starts with 2N that I've come across so far, the pin on the left when you're looking at the flat side is the emitter, pin is in the middle is the base, and the pin on the right is the collector. So we're going to put the base where the 2 resistors come, and we're going to put the emitter down here, collector up here, and I spread out the pins a bit so we have a gap so things aren't quite as cluttered. Now here we have a 100 ohm resistor, meter set to measure resistance. You can see mega ohm right there. That's because it's an auto ranging meter, and the air is a lot of resistance, and it's not giving us a reading though. But now you can see that it went to kilo ohms and then now ohms, and so this is 99 ohms. This is a 100 ohm resistor, and this is actually what's going to set the current. So we set the voltage to the base of the transistor, and that voltage minus about 0.7 volts drop at the base there, base to emitter, is going to be across the resistor. We can't really measure that now because now that it has a current path, the voltage, it's going to look different and at the output there. But it's not going to behave like that in the circuit. We'll see that coming up. So now I have the meter set to measure milliamps. It's an auto ranging meter, and other than high current, we just keep the red probe in the same spot there. You can see the milliamp setting, which is more than microamp. So even if you do microamp, you keep it in the setting. But there you can see it says milliamp next to there. And let's shuffle that over. There you go. That looks good. So here's the main takeaway. We're going to measure the current now that the transistor allows through from collector to emitter. Now you can see that's 17.89. Now let's get an LED here and put that in series with the transistor. And normally when you put something in series with another component, the current goes down. But there you can see the current is basically exactly the same. Now let's grab a resistor and do the same thing. So again, this is a 100 ohm resistor, I believe. and there you can see the current's the same, 17.86. So the current's holding steady. Of course, that's only if the load doesn't block more current than what you are running through there. And let's take a look at the resistance of this resistor. Pretty sure it's 100 ohms. Yep, 100 ohms. So let's move the resistor over one spot. We're still not at that rail though, and put the LED in there, and jump this back to measuring milliamps. And now you can see it's quite a bit less. So not a whole lot less, but it is less. It's not constant anymore. So at 5 volts, with this setup at least, we really reached our limit. And there wasn't much I could do with 5 volts. That's why on the sheet and the upcoming circuits, I use a higher voltage. So now what I did was I have the transistor setting the current for the LED, as we saw before. And let's take some voltage measurements. So first let's get the base of the transistor, and we can get accurate measurements now that the circuit is working. But there you can see it's the 2.5 volts that we set before. And the base to emitter is dropping about 0.7 volts, which is to be expected. Now let's go across the resistor here. So 2.5 minus 0.7 should give us, what, 1.8, I think. And that's about what we got. Close enough. Now let's yank the LED out of there. And now that there's no load, of course these numbers, they're not going to match up. There you can see we only got 1 volt there. We are still blocking about 0.7 volts in that range or whatnot. And here, and that's because the transistor is not running, and so the voltages aren't building up. But let's put a resistor in there, and the pins are coming at a different angle. There we go. So they weren't going in terribly easy. But anyways, let's look at the there again, the base is about 2.5 with about 0.7 from base to emitter, and then we'll see the same voltage across this resistor. And it's the voltage across this resistor and the current that it is letting through that ultimately decides how much current can run through here, as long as the load doesn't limit it even more. So now, that didn't give us much voltage to work with. We couldn't do much, but we'll be able to do a lot more with this power supply. So let's turn everything down and then hit the power button. There we go. And let's turn it up a little bit. Turn the current up a little bit. This will limit the current, but basically we want to see the voltage there. So we're going to start off with 10 volts. I can do a lot more with 10 volts than 5 volts. And we'll set it up to 10 volts there. And no current is flowing because the alligator clips are floating. I made sure to check that before I turn the power supply on. And let's turn the current down, and we can attach the alligator clips directly together. So now we have a short circuit through there. You can see that the voltage went down. Probably hardly any currents flowing. I bet a little bit is, but in any case, we'll keep those two clipped together, and we can turn up the current. And this is a short circuit, so it's telling you about how much current is flowing through, about 100 milliamps, which is actually going to be more than we need. Let's set it up to 400 milliamps of current. There we go. And that's all this power supply is going to allow to flow through. Once we unplug it, now there's no current flowing, so it can measure the voltage on there. So we can actually keep an eye on the voltage, but it's going to be too hard to put this and the circuit on camera. So I'll just tell you what voltage I have it set to from now on. And that brings us to the first circuit we have for the schematic diagram. And it's basically the same setup, but we're dealing with 10 volts. So we're going to use higher resistance, 10 kilo ohms, to make the voltage divider, a pair of them. and then 1 kilo ohm to set the current. And the base there, I have the transistor already on the board. The base, the middle pin, I have this jumper so that I can set the resistors and stuff over there, because I'm going to put a lot more stuff for a load off to the side. But anyways, collector's up above, emitter down below. I have these two jumpers so that if we power one rail, the other one's powered. Same with that. And at the rails, I have these alligator clips, which I will clip to the clip of the bench power supply. I added the two 10 kilo ohm resistors as a voltage divider, one to the positive rail, one to the negative rail. They both come here to that jumper, which I said goes to the ground pin, or the base pin of the transistor. And now I have the emitter resistor there, which is actually going to set the current. There you can see there at the emitter, goes to the negative rail, or ground. And so we'll have 5 volts at the base, because we're using a 10 volt power supply, 2 equal value resistors, and it's dividing that, so it divides it in half. We lose 0.7 volts, so that will leave us with 4.3 volts. You divide that by 8,000 ohms, and you'll get 4.3 milliamps, which is the same as 0.0043 amps. And so now I turn the power supply on. I have a jumper up here. Let's zoom back a little bit. But we have it set to measure milliamps, so I'll put the positive there because the current has to go through the meter. And then we'll go to the collector of the transistor there. And there you can see 4.26 milliamps, which I calculated to be about 4.3 milliamps. So we're looking good there. So now, that was with no load. I added 3 resistors. They all go to the collector of the transistor. That's why I have it pushed off to the side, and a little jumper for the base. But in any case, we have here a 100 ohm resistor, a 220 ohm resistor, and a 470 ohm resistor to give us different values. And there you can see the current is still 4.26. It's holding steady even with these different resistances. And now I added LEDs in series with the resistors, and as we saw in the 5 volt circuit, that was too much, so we upped the voltage. And remember, with LEDs, they're a type of diode. They only conduct in one direction and light up when they conduct, and so the long lead, the anode, needs to be more positive. Short lead, the cathode, needs to be on the more negative side of the circuit. And so let's see what we got here. Again, 4.26, 4.26, and 4.26. We're still looking good. Let's add another LED in series. So now we got 2 LEDs in series with the resistor before it gets to the transistor. Let's check the 100 ohm resistor, 220 ohm resistor, and now the 470 ohm resistor. And as you can see, we lost a little bit of current there. So not much. This is still pretty close, but it's not as steady as these less demanding circuits. So that's about where we're reaching some kind of limit. And so we could step up the voltage. In fact, I'll do that quick. I'll do 12 volts. And so the current's going to be different, but I'm guessing it's going to be the same across all 3 of these circuits. So 5.23 now. That's because our voltage got closer to 6 volts. We're at 12 volts. It's 6 volts coming there, minus 0.7 volts. So that makes sense. 5.23 milliamps because we got a 1000 ohm resistor setting the current. And there you can see, now it's 5.23. So to keep the current the same with these, we had to step up the voltage from 10 to 12. And I found that's a common solution. And we could use different resistors or a Zener diode to change the voltage. And so I drew this little schematic down here to show how you use the Zener diode there. In fact, I wrote it down. I'm going to use a 5.6 volt Zener diode right there. And I found that it works best if I have at least a 12 volt power source. That's why I already did this, and we just set it to 12 volts. So that's good. So all we gotta do is yank out the resistor at the voltage divider that goes to the negative rail there, and we need to reverse bias the Zener diode. I'm going to turn the power supply off, make sure I don't short circuit something. And the cathode is the black stripe on there, and you can't read on here what its value is. I took it out of a baggie. I took it out of this baggie, in fact, and it says 5V6. That's for 5.6 volts. A lot of times they use V in place of the decimal point because you might not see a decimal point right there. So 5.6 volts, that's how much it blocks while it's reversed bias. Remember, we have about a 0.6, 0.7 volt drop at the transistor base to emitter, and so we'll have 5.6 volts there minus about 0.6 volts to make the math easy, which will give us 5 volts. And let's slide that in, and that's even with differing power source voltages. There we go. So make sure it's reverse bias. Cathode now goes to the positive side of the circuit, whereas the anode goes to the negative side. That's just how Zeners work. And so now we got the meter back. Let's turn the power on. There we go. And first thing we can do is measure the rail to show that we're dealing with 12 volts there, so 11.99. And let's go across the Zener. So again, this is the more positive side. We're going to look at the voltage across the Zener, which should be about 5.6 volts. And for some reason it's not. That's because it's dropping through this resistor here, because we don't have a load. That's why. So yeah, be careful when you take your measurements. If it looks off, there's probably a good reason. So now there's that load going through the transistor now, and you can see we got about 5.8 volts, it looks like, across the Zener diode. So they're not 100% accurate, but in any case, it's close enough. So let's put that jumper back, and now we're going to take a current measurement. We should be dealing with about 5 volts. Sorry about the loud beeping. We should be dealing with about 5 volts across, because remember the diode drop of the base to emitter. So about 5 volts across this resistor. So that's going to lower the current down to about 5 milliamps. More or less, but pretty close. So let's see what we got here. There you can see 5.15 milliamps, so close enough. There you can see there. So yeah, this is pretty reliable. There's some things though to be aware of, so hopefully you pick those up. I learned a lot just doing a bunch of practice circuits to prepare for this video, you know. So build some circuits, start simple like I did, and work your way up. And so talking about the Zener, now we're going to come back to the 5 volt circuit, which I don't think really any Zener is going to work good for because of the 5 volts. Maybe it will, but I haven't had much luck so far. So I'm going to take out the resistor that goes to the negative rail, and I'm going to take a couple of rectifier diodes. And so they're the ones that we commonly use. This time we're going to forward bias them. We want them in the direction that they're going to conduct better, because they still block about 0.7 volts, as does the Zener diode. If you forward bias, its voltage is based on its reverse bias. These block probably over 50 volts before they start conducting if you reverse bias that. You don't want to do that with rectifier diodes though. You'll probably destroy it. But Zener diodes are made to conduct while reverse bias. For a certain amount of current, they have a wattage rating. And so we're going to take a second one now, because that is just on a blank row. That's why I spread out the pins of the transistor there. And now we're going to ground this. So these voltage drops are going to add up. So we got about 0.7 volts each, and so they're going to drop, they're going to block about 0.7 volts each. So it's going to block about 1.4 volts, which remember the base to emitter is going to drop about 0.7 volts of that. So we should end up with about 0.7 volts at the emitter when we're done. And that should be the voltage we work with when we have the 100 ohm resistor. So we should expect about, what is that, 7 milliamps of current, I believe. And so now I plug the barrel plug back into the power supply. Power supply is on. Let's take a look at the current that we're getting there without blocking the meter, if I can. There we go. I have the probes backwards. It's negative 0.63. If I flip them around, luckily it's safe to measure voltage backwards. You just get a negative number. So there we go, 6.32. Let's add an LED to the collector. Don't want to go into that spot. Let's jump over there. There we go. Don't fight with the hole if you have another one to pick from. There we go, 6.3 volts. Now let's add the resistor here. I'll try to make the pins a little straighter for if you have them kind of at an angle because they were in a wider or narrow spot before. They don't tend to go in as good, and these pins aren't very stiff, but we should now still have about the same current there. And so I found that not only using a higher power source voltage, but actually setting your voltage lower for a given power source will help make it where you don't lose current at a point. It'll make it work a little bit better as a constant current source. And so for the next readings, to save time, I connected the resistor directly to the jumper there. So now the transistor is passing current, because as we saw before, to get accurate voltage measurements you actually have to have the circuit working. So first let's go to the negative rail and check the voltage at the base. This is set by the two forward biased rectifier diodes. One's blocking about 0.6 volts, 0.7 volts, in that range, and so is another one. So you add them up, where it's going to block about 1.2 to 1.4 volts, and looks like it's about 6.5 or so. But in any case, now we go base to emitter, and you can see that's dropping about 0.681 volts. So we go to the emitter, which goes to the resistor. We could measure the resistor directly, and you can see we got the other half of the voltage across that, and that's actually what's setting the voltage. So 0.63 volts divided by 100 ohms of resistance gave us our about 6.3 milliamps of current. And now down here we have a trim pot here, because a voltage divider should work pretty nicely in this circuit. We can set the voltage anywhere. Since we're using a 12 volt power supply, we could set it anywhere down to 0 volts if we turn the knob down there, or all the way up to 12 volts if we go up there. So VCC means you don't have a specific voltage you're working with, and it says VCC because it's on the side of the collector for an NPN transistor. Unfortunately, it's not the collector side for a PNP transistor, which we aren't doing in this video. It's actually on the emitter side. But when you see VCC, that means the collector side of the NPN transistor, which is the more positive side of the circuit. So it's always the more positive side of the circuit. But in any case, we have the trim pot here. We can set the voltage, which I'll do coming up, and then take this jumper here and put it up there. So now, to save time, I prepared the circuit. I got rid of the Zener and the resistor over there. Now I have this jumper, which I can just plug into there whenever I want. Let's. I already set this to 5.6 volts, plus or minus a little bit. There you can see there. And I'm finding it's not near as accurate if I go above this. So looks like you want to stay below halfway of the power supply, at least for this particular circuit. So there we go, with a 1 kilo ohm resistor there. That should give us about 5 milliamps of current, plus or minus a little bit, through each of these. So let's check that there. So pretty much 5 spot on. That's 4.93 though. 4.93 and 4.93. So now I'm going to unplug this and set this to 6.6 volts. And now it is 6.6 volts. And to spare you from the beeping, I'll jump ahead and set the meter to measure current, which it is now set to do. So we expect with 6.6 volts at the output here that we will get 6 milliamps of current more or less through each of these. So let's see what we're actually getting now. So 5.8. So this should all be equal. 5.8. Whereas that one's 5.46. So let's get rid of one of the LEDs. And because if we make the loads a bit less demanding, they have voltage drop, which complicates things. But in any case, there we go. Again, 5.83, 5.83, and 5.83. So the load makes a difference. But in any case, hopefully this was helpful for you. I learned a lot preparing for this video, so I hope you enjoyed it and learned a lot too. Thanks for watching.